Hey, that looks good. I got up to go to the bathroom, and I came back and there were all these questions, so this is good. So we'll turn off this music. I could listen to this music all day, but I know people hate it. Doot 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 doot. Okay, we'll stop with that. Hi, welcome to the review. So before we start on the review, just a few things to note. Course evaluations are due Friday. Make sure you turn those in by Friday night. Do them early in case you have trouble logging in. I haven't actually looked at any of the numbers yet. I try not to because they just constantly change. So getting any update right now doesn't tell me anything. Again, I don't see the evaluations until after the course is done and I've uploaded all your grades. So I have no idea what you wrote. Please be candid and honest. Last call for quiz number 8. That's tonight. Make sure that you get that done. You can ask me questions on chapter or quiz 8 content. That's fine. Because we'll do problems that are similar to them here anyway. And then lab worksheet number 5 is due next week. That's on a Tuesday. Last call for that is on the day of the final, so better to get that done earlier rather than later. Also, doing lab worksheet number 5 will prepare you for the questions from Unit 16 on both the exam and the final. So that could be a useful exercise to do too. Review the lecture from yesterday if you need to have more information about how to do the labs. You can ask similar questions to the labs here, but for today, the purpose of the review is not to do the lab. It's to do any other questions that you might have, and here are a bunch of them that you can see here. So now this is inevitably going to scroll down, so what I will do is I will try to keep the question that I am working on the chat at any given moment. Ooh, my cursor's over here. Now it's over here. Because my monitor setup is really weird. Okay, so let's get started right away. So the first question I see is, how many grams of carbon are in a sample of 47... Let me try that again here. 47.6 grams of H2C2O4. So this looks like... That's funny that there's two questions about oxalic acid right next to each other, because this is oxalic acid. So I want to know from grams of oxalic acid... I got confused at first. I was like, are these the same question? No, they're totally different. I want to know how many of those grams are carbon. And so, just like everything we've done for these last few sections, we're going to turn everything into moles. And then once we know moles, you can find moles of any of these things in here. So H, C, or O. We want moles of C, because that's going to tell us grams of C. So let's go and write down all the relationships that we know. So we know how many grams there are of oxalic acid in a mole. And you get the number of grams by looking that up on Lentech or using your periodic table and adding all those elements together. I don't have Lentech open, but I just hit L now, and it appears. Because we've done so much of this quarter in all of my classes. 90.03 is what it says here. Although I guess I could have read that in the next problem, huh? All right, so 90.03 grams of oxalic acid per mole. And then I know that in a mole of oxalic acid, in one of these, how many carbon are there? Well, it looks like there are 2. So per mole, there are 2 moles of carbon. And then I also know that in a mole of carbon, there are 12.01 grams of carbon, because that's right off the periodic table. So now I can take this number, which I'm going to actually move here real quick. Oops, that's not what I wanted. Put that back. No. we'll move this down here. Okay, hopefully that worked. I didn't accidentally hit another key there. Paintbrush, there we go. All right, so we'll turn, oops, wrong color, hold on. We will turn grams of oxalic acid into moles. So grams of H2C2O4 into moles. That's the wrong element. There we go. So that those cancel out. And then we'll turn moles of oxalic acid here into moles of carbon, because that's what we're looking for, right? And then moles of carbon into grams of carbon. We're just going to follow our blueprint here, flowchart, that we've been doing all along. And now we just run the numbers. So in 1 mole of oxalic acid, there are 90.03 grams. So 1 mole, 90.03 grams. In 1 mole of oxalic acid, there are 2 moles of carbon. And in a mole of carbon, there are 12.01 grams of carbon. So we can type all of that in. I'm combining words today. I was going to say type and punch, and I got touch. Put all that in the calculator here. 90.03. I get 12.7 grams of carbon. To 3 sig figs. So there we go. Now that checks out because we should have a smaller amount of carbon than we do of the whole sample. Now you can do this with a mass percentage. If you knew the mass percent of carbon in this sample, like Lentech will tell you, oops, if I can click on it, that the sample is 26.68% carbon. So you could just say, oh, okay, whatever 47.6 is times 20, whatever that percent I just said was. But this is the way to do the stoichiometry. And I do it the long way so that you understand how to do these conversions, because we use these conversions for so many things that the more I do it and the more you get exposed to it, the more you learn how to do it too. So, all right, so for question 2, and this is kind of a coincidence, what is the formula of oxalic acid? Well, it's right here, right? But no, we're going to actually solve that. So we should get that as our answer. So let's do that. I don't know if this is going to be enough space. So you can pause the video if you need to keep this on the screen. Oh, I must have made a new layer. That must be what happened. Wow, I made like all the layers. Hold on. I have too many layers. Okay, so now it should just all go away. All right. So I know that the mass percentage of oxalic acid is 2.240% H, 26.68% carbon, and 71.08% oxygen. And so what I'm going to do is I'm going to say, okay, well, if I have a 100-gram sample, I can only go in one direction with these curly brackets. There we go. So in 100 grams of this, I would just have these percentages as grams, right? So we'll just do that. And then what we'll do is we'll just turn everything into moles. And once everything is in moles, we can compare everything and make a pseudo formula. Because moles are a unit of counting, right? And so if I divide out the moles, I should get the formula. That'll lead me to the answer. So let's do that. So 2.240 grams of hydrogen. We'll turn that from grams into moles. And how many grams are in a mole? Well, if you look on the periodic table, it's 1.008. So 2.240 Divide by 1.008. And I should get like 2. Oh, 2.222222 forever. 2, 2, 2. Too many 2s. Sometimes I wonder when I write these problems if I do this on purpose. Like, I just pick random numbers, really, but it seems to work out like this more often than it doesn't. So let's do the same thing for carbon here. We'll turn it into moles also. When in doubt, turn it into moles. See if that tells you anything. So, 26.68 grams. How many moles is that? Oh, look, it's 2.222. Well, 2.221, actually. And we'll do the same thing for oxygen. Well, if my pen doesn't get stuck on the tablet. I'm writing at like the very bottom of the tablet and my hand has nowhere to go, so like it can go off the desk. I guess I could just do this. I don't know if you've ever written on a chalkboard or a whiteboard. When you're like writing below your waist at the bottom of the board, it feels really awkward. That's kind of what happens when my hand is like off the desk and trying to write on the tablet here. That's something I haven't done in like a year and a half, write on an actual board. That's going to be really weird going back to the classroom. 4.443 is what I got for that. And you could probably already see the relationship that's going on here. So H 2.222, C 2.221, O 4.443. We're going to divide by the smallest number. I'm just reading your comment here. Is it safe to divide the element weight in grams directly by the atomic mass of the element without the conversions? I would just write out all of the units every time, just in case, like if you accidentally hit the wrong key on your calculator. Like if you timesed it instead of divided by, and then you might not know. You'd get a ginormous number and have no idea what went wrong. So stick with writing out all the units, because the conversions aren't there. I'm not trying to make you guys do busy work. I do it this way every time because I want to make sure I get the right answer. Like, I could do this all in my head, I suppose, but the odds of me making an error and then being like, oh shit, what did I do? And then having to go back and debug the error, that would waste more time than I would save. So I just write it out every time. And that's how I get the right answer every time, is I do all the steps. So I'm going to divide by the smallest number to get my actual formula. So 2.222 divided by 2.221 is essentially 1. And then carbon is also 1. And then 4.443 divided by 2.221 is very close to 2. So this is my empirical formula. Now, if I type this into Lentech, HCO2, the number it gives me is 45.02 grams per mole. So if what I put in the detector or the analysis, whatever device that I'm using, was actually HCO2, it should weigh 45.02. But we found that it doesn't weigh 45.02. It instead weighs 90.03. So we have to have some sort of multiplier going on here. So let's figure out what the multiplier is. So the multiplier, N, will be the molecular mass divided by the empirical mass. And the molecular mass is what the mass of the thing actually was, 90.03 AMU. AMU and grams per mole are the same thing. The empirical mass is just what we just calculated by punching in our empirical formula here. And when we do this, we find that 90 divided by 45 is just 2. So what that means is my empirical formula needs to be multiplied by 2 to get the actual formula, because 45.02 times 2 would be the 90.03 we expect, right? So we'll multiply each of the components by 2. So H becomes H2, C becomes C2, and O2 becomes O4. And hey, that's the thing I circled earlier. Look at that. It worked out. Cool. All right. Again, pause the video if you still need this, because it's gone. You can always just rewind back a few seconds. So, all right. So what is the mass of a single phosphorus atom? So 1 atom of phosphorus. Now, a lot of people get confused by this, because if I asked you to tell me the mass of like 2.674 times 10 to the 21 atoms of phosphorus, you'd immediately know what to do. You'd say, oh, well, I'll turn it into moles, and I'll turn it into grams, right? Now, it turns out that when you're just doing 1 atom, you do the exact same process. It just feels really weird, right? So if you know the number of atoms of phosphorus, you can turn that into moles, and you can turn that into grams, right? Well, let's just do that. So we'll turn atoms into moles, and we'll turn moles into grams. And obviously, we're going to get the tiniest number, right? Because atoms are super small. How many things are in a mole? Well, there's Avogadro's number. And then how many grams are in a mole of phosphorus? I don't actually know. I got to look that up. 30.97. I put it right on top of the calculator. That's a great spot for the table. And there you go. So you're going to type in 1 times 30.97 over Avogadro. And I got 5.143 times 10 to the minus, is it 22? 23 grams of phosphorus. So that would be the mass of 1 atom of phosphorus. And it should be real darn small, right? That's pretty small. All right, where are we now? So now we're here. What mass of oxygen in grams is contained in 1 liter of pure water? Here's its density. All right, so if I have 1 liter of H2O, so that's a volume. So with a volume of water, I could figure out the mass of water, right? Because that just uses the density. And if I know the mass of water, then I can just do this stuff that I'm doing up here again, right? So we can turn this into moles. And once I know the number of moles of water, I know the number of moles of any component of it, right? So that would tell me the moles of oxygen, which would tell me the number of grams of oxygen. Oh, we got scrolling going on, so I'm going to scroll back up here. So keep typing questions. They'll just be down here, and we'll get to them in a second here. So how many grams of water are in a mole? I actually have that one memorized. Let me get a different color here. So mass of water per mole is 18.02 grams of water per mole. I also know that in 1 mole of water, how many O are there? Well, there's only 1 written there, so we'll say 1 mole oxygen. And then for moles to grams, 1 mole of oxygen is 16 grams of oxygen. Be real careful you don't accidentally put 32, because we're just looking at oxygen, the atom, by itself. So we have all sorts of conversions to do here. I'm going to just move this guy down here. So I've got 1 liter of water. Now, in order to use the density, you'll notice that the density is in grams per milliliter. So I got to first do liters to milliliters here to make that work out. And then once I know the number of milliliters, I can then use the density to get grams of water. So this is all that density part. You need those 2 steps. Then, once we've got grams of water, we can do moles of water. And once we've got moles of water, we can do moles of oxygen. And finally, grams of oxygen. And so now we're just going to fill in all these numbers to get our grams of oxygen. So a milliliter is 10 to the minus 3 liters. The density of water was 0.9983. There are 18.02 grams per mole of water. And then in every water, there is 1 oxygen. And 1 mole of water, 1 mole of oxygen is 16 grams. That should be a dot. There we go. So all sorts of numbers to punch in now. Most of them are 1. 10 to the minus 3 times 18.02. There. I got 886.4 grams of oxygen. So, for reference, 1 liter of water is very, very close to a kilogram. And so we should expect most of water to be oxygen anyway, and 886 grams is very close to a kilogram. So our answer makes sense for a rough estimate. All right, so that's that one. All right. How many pounds of sugar can be produced? I'll just get all the questions on here. Now there's a giant arrow in the way. That's fine. How many pounds of sugar can be produced from a quantity of 2.638 times 10 to the 25 atoms of carbon? So I'm going to hit clear again. Boop. I don't know why my Photoshop does that plus thing through the middle. You know, I should just start this down here. 10 to the 25 atoms of carbon. And so, whenever you have atoms of something, well, something, we've done this for every time we have atoms, turn into moles, right? Now, if you know the formula for sugar, which wasn't written on the problem that you gave me, but the formula for sugar is either this is glucose, or it's this, which is sucrose, which is table sugar. So depending on which one it is, it's going to matter. So if you know which one it is, let me know so I can solve the problem, because the next step here is to go from moles of carbon to moles of whatever our sugar is that we're looking at. So if you can be more oh, so it is sucrose. Okay, so it's this one. That's the more common one. Like, you don't eat glucose. You get glucose from various things, and sucrose is partially glucose. The other part is fructose. Or maybe it's two glucoses linked together. I don't know. I'm not a biochemist. I just look this stuff up. So, if we know the number of moles of carbon in there, we could say, oh, okay, well, that came from sugar, which is sucrose right here. And then what I can do is I can turn that into grams. And then once I know the grams of something, I can turn it into whatever mass unit I want to. Oh, I don't know what my 2 did there. There we go. So now that we know our path, let's go write in all the conversions. So we know that there are Avogadro's number. My pen. Atoms of carbon in 1 mole of carbon. And then I know that in 1 mole of this big thing, there are 12 of these. So 1 mole of sucrose has 12 moles of carbon in it. In 1 mole of sucrose, there's some number of grams of it. And I gotta go look that up, so we'll type that into Lentech here. Oops, that's not Lentech, that's the broadcaster. C12H22O11. Mine said lactose, but I think it's the same thing. Yeah, it just hit the first thing it saw. 342.30. Photoshop, there we go. And then grams of anything and pounds of anything, we can look that up. So 453.6 grams per pound. There we go. So we have all the conversions. So you could see that these problems are basically just testing you on stuff that we've already done, and then trying to tie it back to all the original stuff that we did in like chapter 2 and 3. So atoms of carbon will be moles of carbon. Moles of carbon can be converted to moles of sucrose. I'm going to run out of space here. Moles of sucrose. I wrote the wrong thing, sorry. C12H22O11. We can turn that into grams. And then we'll multiply it by our conversion from grams. I keep writing 22 to pounds. Okay, let's go fill in all these numbers here. So atoms to moles, that's easy enough. In 1 mole, there are Avogadro's number. In 1 mole of the big thing's up on top this time, there are 12 moles of the carbon that we were given. And then in 1 mole of fructose, we have 342.30 grams. And then there, in 1 pound, there are 453.6 grams. So this should be number of grams of sucrose that are in this sample that contains this many atoms. So 2.638 times 10 to the 25 times 1 times 1 times 342.30 divided by Avogadro. I typed too many zeros there. Times 12 times 453.6. And I get a 2.755 pound bag of sugar. Not a conventional unit that we sell sugar to you in, but that's what we got. All right. I'm going to clear this out again, since I need it for the industrial production of sulfuric acid. Ooh. Now you know all the secrets of industry. So first we got to write out the equation. So we need a sulfur, and we need an O2. We need a water. There you go. Now, unfortunately, I can't just do 1, 1, 1, 1, 1 all the way across, because that would get H2SO3. So I need an extra oxygen in order to do that. But if I do 2 here, then I have to put a 2 here, and then everything gets screwed up again anyway, right? So let's see here. So I need 8 oxygen, and I have 2, so I need to do this. There we go. So 2 sulfur on both sides, 4 hydrogen on both sides, should be 8 oxygen. So 6 times 2 is 8, and then 2 times 4 is 8. Cool. So there's our balanced equation. And I'm going to put 20 grams of sulfur in and 20 grams of oxygen. And we're going to find out which one is the limiting reactant. So if we're making sulfuric acid, we're going to turn grams of our starting material into moles, and then we'll do moles of that into moles of sulfuric acid, and moles of sulfuric acid into grams of sulfuric acid. And we'll do that for both of these. So grams of sulfur, moles of sulfur, moles of sulfur, moles of sulfuric acid. And then finally, moles of sulfuric acid into grams of sulfuric acid. And we're going to do the same thing down here. I'm just going to set up all the units while I'm thinking about it. So grams of starting reactant into moles, and then moles of that reactant into moles of sulfuric acid. And then moles into grams. There you go. So now we're going to go and fill in all the numbers here. I'm going to do the top part and just solve the answer, and then we'll do the bottom one. So according to the periodic table, in a mole of sulfur, there are, is it 32.06? 32.07. And then in 1 mole of sulfuric acid, there is, oops, hold on. Sorry, I was doing an empirical formula here. So we put in 2 moles of sulfuric acid and 2 moles of sulfur. So I'm going to put a 2 and a 2 here. Now, I could have just done 1 and 1, but I wanted to be consistent. So we're using the coefficients because we have an equation here. And then for sulfuric acid, 1 mole is, oh, hell if I know. Let's type that in. Lentech, what do you got for me? H2SO4, 98.08. So 20 times 2 times 98.08 over 32.07 times 2. Now these 2's cancel out, so you don't actually have to punch them in. And I got 61.2 grams of sulfuric acid. Could be made if I threw in 20 grams of sulfur and everything else is in abundance. But that's not the case we have. We don't have oxygen in abundance, nor do we have sulfur. So we need to compare the results of the oxygen to see which one's the limiting reactant. So we can do that. In a mole of oxygen, there are 32 grams. Right off the periodic table, so I took oxygen times 2. For every 2 moles of sulfuric acid I put into the equation, I get for every 2 moles I get out of the equation, I put in 3 moles of oxygen. And then the molar mass of sulfuric acid is still 98.08. And we'll punch that in the calculator. And down here I got 40.9 grams of sulfuric acid. So which one is the limiting reactant? It's the one that makes less of the stuff, right? So this is my limiting reactant. The other reactant must be in excess. What do we do with excess? We scribble it out. We don't use it. It is not the answer. So there you go. So the limiting reactant was oxygen in this reaction. And if I put 20 grams of oxygen and 20 grams of sulfur in, I would get 40.9 grams of sulfuric acid out and some leftover sulfur because sulfur was in excess. I would need to supply more oxygen to react with that. Excuse me. There we go. Okay, so let me go back over here. Boop. Oh, that was it. Okay, cool. So we're at break time anyway. So if you have any questions, let me know. I'm gonna put this back on the screen here. Did I reset the timer? No. There we go. So I'm gonna put the Insidious music on. It's so catchy. And then please ask me more questions if you have them during the break. We'll come back in 10 minutes. If nobody has any questions after 10 minutes, we'll do final concluding remarks and so on and so forth. So I'll see you then. Hi, everybody. Last call for questions. Please type any questions you might have in the chat. Hi, everybody. So, last call for questions. If you have any questions, now's the time to ask them. Well, if you find them and the session ends, that's totally okay. Send them to me over email or Discord, and I'm happy to answer anything over email. Yeah, anything else? Okay. Well, if everybody's good for now, then let's do the closing thoughts and stuff. I do want to thank everyone for coming out to the review session. I hope that was helpful. Exam number 2 is on Friday. It will open on Friday. Make sure you get it done by then. If you need it moved to Thursday or Saturday, please email me and I will do that. There will be a final exam review session on Tuesday next week. I think it's Tuesday. It's in the syllabus. So if you have any more questions, you can always ask them then, and that'll be for the entire quarter, units 1 through 16. You can ask anything about that. But until then, best of luck on the final or on the midterm. Make sure that you do the course evaluations, get that quiz in tonight, and work on the lab worksheet number 5. And thank you for being a part of this class. I know that it's difficult to be an online student. It is, in some ways, more difficult to be an online instructor because it's hard when not everybody is there. But for everybody who has participated in the chat, participated in the Discord, sent me emails, or whatever, I really appreciate it. You've made my job a lot easier and a lot more meaningful. So yeah, that's all I have. Have a wonderful rest of your week. Best of luck on the exam, and if this is the last time that we see each other, I wish you all the best of luck from here on out. Take care, and I'll see you again someday.